We're going to open our discussion of modern physics looking at the rectangle of physics. Everything in the universe fits into one of these four boxes. The boxes are labeled by size and by speed. When we look at the speed, what we're looking at is the speed compared with the speed of light. So by slow, we mean speeds much, much less than the speed of light. And by fast, we mean speeds that are approximately the speed of light, definitely less than the speed of light, though, like we'll see in a few minutes. By big and small, we mean compared with the object's own wavelength. Now, it's a little bit weird to talk about an object having a wavelength. Usually we talk about waves having a wavelength, but we'll look at what that wavelength means. We as human beings live in this corner. We are slow compared to the speed of light, and we are incredibly big compared with our own wavelength. So this is us. This is the domain of non-relativistic, classical mechanics. This is everything you learn in Physics 1 and pretty much everything you learn in Physics 2. So all that entire year of intro physics, you are in this one corner of the universe. Today, we're going to take a look at what happens when big things start moving fast. This is what happens, for example, when we are looking at galaxies, or when you're near a black hole. This is the domain of relativistic classical mechanics. In other words, the laws are still the same. The universe is still behaving classically. There are still forces and momentum and kinetic energy and all that great stuff. It's just getting modified by relativity. Really what's going on is that this is the real case, and we live in the special case where speed is much, much less than c. The other half of the rectangle of physics involves things that are small. So when things are slow and small, that's the domain of things like electrons. So if you really want to describe how electrons move around in a circuit, you actually have to take into account the fact that they are very small and start using non-relativistic quantum mechanics. Right? So the speed determines whether you are non-relativistic or relativistic. See how this one's non-relativistic, this one's non-relativistic? The size determines whether you are classical or quantum. See how both these are classical? This one is quantum. So in physics, quantum is the opposite of classical, or classical is a very limiting case of quantum mechanics. Again, this is the real fundamental reality. And we live in the special case, right? We tend to think of our everyday experience as the default and these as the weird things. But in actuality, these two are the way the universe actually works, and we live in the special case of being slow and big. Now, there's a fourth quadrant here for things that are fast and small. This is for things like particle colliders, like the LHC. You might intuitively think, okay, I'm fast, so that makes me relativistic. And I'm small, so that makes this quantum mechanics. And so you might think, like many physicists at the beginning of the 20th century did, that this would be the domain of relativistic quantum mechanics. But it turns out that if you just take your relativity from here and your quantum mechanics from here and you just kind of mash them together, you actually get an infinity. And so relativistic quantum mechanics actually makes the universe blow up. We actually have to start from scratch. We have to go down to basic principles and start with something called quantum field theory. Again, it's really weird to think about, but quantum field theory is actually the real basis of reality, and we live in an intersection of two special cases. One of the consequences of this is that anytime we go exploring in these three quadrants of the universe, things are going to look weird. And so in a modern physics class, one of the things that you can expect is for the universe to start to look very weird compared with your everyday experience of the slow, big universe. So we're going to start our exploration of modern physics looking at relativistic classical mechanics by taking big things and making them go fast compared with the speed of light. Now you might wonder, why is the speed of light so special? Why is it the speed of light on this axis and not the speed of sound or some much bigger speed that's even faster than the speed of light? Well, there's three reasons that we're going to talk about today why it's the speed of light on this axis and not any other speed in the universe. For one thing, the speed of light comes out of Maxwell's equations as a special invariant property. You might remember Maxwell's equations from Physics 2. There is Gauss's law, for example, the integral of the electric field dotted with a closed surface equals the amount of charge enclosed by that surface divided by epsilon naught. So this is the electric field that's produced by some charge distribution measured around some imaginary surface you're drawing. And this epsilon naught is a fundamental constant of the universe. You also might remember the similar Ampere's law, that the integral of the magnetic field dotted with a loop, so now instead of a surface it's a loop, is equal to the amount of current enclosed by that loop times mu naught. And this is the magnetic version of epsilon naught, right? This is the Greek letter for E, this is the Greek letter for M, E for electric, M for magnetic. They are both constants of the universe. What's special about these two, if you combine Maxwell's equations together, the solution is an electromagnetic wave with a speed equal to 1 over square root mu naught epsilon naught. If you calculate this and compare it to some data from optics experiments, it turns out this thing is the speed of light, c, 3 times 10 to the 8 meters per second. What's special about this is that we're not specifying in Maxwell's equations who is doing the measuring, right? Maxwell's equations are true whether I am standing still relative to the experiment or whether I am moving at half the speed of light relative to the experiment. In other words, no matter how fast I am moving, the speed of light is going to be the same in any reference frame, which is already weird because in the big slow world that we're accustomed to, I would add those speeds together, right? Think about when you are in a car moving at 45 miles an hour next to another car that's moving 45 miles an hour, you perceive that car to be stationary with respect to you. Or maybe you're going 45, they're going 50, you see them creeping past you at 5 miles per hour. We would add those velocities. On the other hand, Maxwell's equations tells me that the speed of light is not going to add like that because it's going to be the same no matter what reference frame I'm in because I never specified a reference frame in Maxwell's equations. Another reason that the speed of light is our special velocity scale is because photons have no mass. Right? The photon is the fundamental particle of light. We're going to learn in a little while why this is significant. But basically, if a thing has no mass, you really can't travel any faster than that. Right? A thing with no mass is automatically going to travel as fast as it possibly can because there's no way I can push it any faster because there's no mass there to push, right? There's no mass there to resist the acceleration or to reduce the acceleration from a force. And so whatever velocity light has, that must be the maximum speed of the universe. The third reason that the speed of light is the special scale in the universe is that the speed of light c governs how space and time transform around me as my velocity changes. And that's what we're going to take a look in today's codes. In order to understand what we mean by this concept of space and time transforming as your velocity changes, we're going to take a look at a simple thought experiment involving two physicists and a train. We have a blue physicist who is on the train. We have a, hold on, I need to get one of them a skirt. There we go. All right, sorry, start over. Stick figures is a great example of where we think something is gender neutral, but it's actually male centric, right? Okay. In order to start with the cap off. In order to understand the concept of how space and time transform as your velocity changes, we're going to start with a simple experiment involving two physicists, a red physicist and a blue physicist, and a train. The blue physicist is on the train and has a flashlight at her feet, a mirror up here, and a light detector right next to the flashlight. What she's going to do is flick the flashlight on to send a beam of light up to the mirror and then back down to the light detector. This is going to enable her to measure the amount of time between when the light leaves the flashlight and when it returns to the detector. So that's a pretty simple calculation to do. Velocity is equal to distance over the time. So the speed of light is c by definition. The distance here is going to be 2 times the height of the train because it's got to go up once and then down once. So that's a total of 2h. And then we're going to divide by the amount of time that is measured on the train. I'm going to specify it's the time on the train, knowing how this problem ends up. So this is the path. The blue line is the path that she sees for the light. The red physicist, on the other hand, sees a slightly different path because the red physicist observes that the train is moving forward with a velocity, let's call it v, and so the red physicist is going to observe a path that looks like this, right? Because as the light is moving up, it's got to move forward to catch up with the mirror and then catch up with the light detector there at the end. And so the red physicist sees a slightly different trajectory. There is still this height h here, but there's also now an additional horizontal component. Let's call that v times the time, v times the time measured from the ground. We're going to divide that by 2 to represent that it's going this half, and then another vt ground over 2 to represent the second half. Well, that's a right triangle. I know how to make that, how to get this total distance here. It's just a Pythagorean theorem. So I'll have an h squared plus this whole thing squared, v squared, time on the ground squared over 4. Take the square root of all that to get the hypotenuse. And we're going to multiply that by 2 because we're going once up this way and once down this way. And that gets divided by the time on the ground to give me the speed of light c. Now, here's the trick. We just argued on the previous board that the speed of light's got to be the same in both their reference frames. In other words, the blue physicist measures a speed of light c, the red physicist measures that same speed of light c. So these two speeds need to be the same. Let's work with this equation a little bit to see what we can learn from it. There is a nasty square root up here, so we can go ahead and square both sides. Over here I'll have an h squared divided by time measured on the train squared. These 2's will cancel, so that's nice. Going to equal h squared plus v squared time on the ground squared over 4, all divided by time on the ground. I can do a little bit of canceling between this tg squared and this tg squared and clean the whole thing up with some negative exponents. So let's try time on the train to the minus 2, going to equal h squared time on the ground to the minus 2 plus v squared over 4, right? This is a distance squared over time squared, distance squared over time squared, and a distance squared over time squared. What you can immediately tell from this is that these two times are going to have different values. Particularly, let's work this off to the side for just a second. H squared, time on the train to the minus 2, has got to be less than h squared time on the ground to the minus 2, right? Because, it's got to be greater than. Because this thing equals this thing plus an extra piece being added. That means this thing on the left has to be bigger than this one piece on the right over here. I can cancel out these h squares, and I can put these folks in the numerator if I flip the greater than sign into a less than. And so what I immediately get out of this is that the time on the train has to be less than the time on the ground. This is already something bizarre here in relativity, because of the different path that the light has to take in order for them to measure this occurrence, this event. Then the time that the blue physicist measures has to be less than the time that the red physicist measures. Let's take a look at how these two times are related to each other. I'm going to bring in an extra little feature here. I'm going to bring in that the h is equal to c times the time on the train over 2. That's just taking this equation here and rearranging it for h, where I'll divide by 2 and multiply by time on the train. That's going to be useful because now I won't have h anywhere in here. So I'll have a c squared time on the train squared over 4, because everybody's getting squared in the h, going to equal a c squared time on the train squared over 4. Time on the train to the minus 2, forgot to copy that. Time on the ground to the minus 2, plus v squared over 4. That's handy because now I've got time on the train squared, time on the train to the negative squared, so those will cancel. And I'll have a c squared over 4. I'd like to go ahead and move this over to the left-hand side as minus v squared over 4. That's nice and symmetric, right? I have a velocity squared over 4 minus another velocity squared over 4. Going to equal this thing together, c squared time on the train squared divided by 4 time on the ground squared. Everybody has a 1 over 4, so I might as well cancel those. Cancel, cancel, cancel. I can also divide everybody by c squared, right? So c squared over c squared will give me 1 minus v squared over c squared. So you can think of this as like the ratio of the velocities, the velocity of the train and the speed of light. Going to equal, cancel those two, time on the train squared divided by time on the ground squared. So if I take that and solve for the time on the ground measured by the red physicist here, I can move this to the left-hand side. So I'll have tg squared. I can take this thing, think of that as parentheses, move that to the denominator on the other side, time on the train squared divided by 1 minus v squared over c squared. So in other words, the time on the ground is going to equal the time on the train divided by the square root of 1 minus v squared over c squared. This gives me the same result that I had before, that time on the ground has to be greater than the time on the train, because this thing, 1 minus v squared over c squared, has got to be less than 1, because it's 1 minus a number. So as long as my velocity is less than c, then this thing comes out to be some number less than 1, right? The square root will come out less than 1. You divide by a number that is less than 1, and you make this number bigger. You make the result bigger, so that t time on the train is less than the time on the ground. Now, this also has the immediate implication that I'm not allowed to have a v greater than c, because then my square root would be imaginary, right? Because if I had v greater than c, this thing would be greater than 1, so I'd have 1 minus a number bigger than 1, gives me a negative. Square root of a negative gives me an imaginary number, and that would mean the time on the ground would be imaginary. We've never observed imaginary time. We don't have a way of measuring it, so that means that the velocity cannot exceed the speed of light. And so this is where we get this notion that the speed of light has to be the speed limit for the universe, because otherwise our time turns imaginary, and that's not allowed. Let's now suppose that these two physicists try to measure the length of something on the ground. Let's say there's a cat over here playing beside the train tracks, out of the way of the train. Cat is safe. What's going to happen to their length measurements? What's going to happen to the length of the cat as measured by the red physicist? And what's going to happen to the length of the cat as measured by the blue physicist? Let's figure this out. Well, distance is related to time by the speed of light, right? So length is equal to c times the amount of time it would take for the light beam to travel across the cat. So that means that the length as measured by the physicist on the ground is going to be c times the amount of time measured by the physicist on the ground. But we've already seen that this time on the ground is related to the time on the train. So we'll have a c times the time on the train divided by square root 1 minus velocity of the train squared divided by c squared. C times this, though, that is just the length as measured on the train. So that's going to get divided by 1 minus v squared over c squared. Now, the cat is on the ground, right? This is where we need to make a distinction of whose reference frame the thing being measured is in. So in this part, in the original problem, the experiment was being conducted on the train. Right? And so the experiment kind of belongs to the blue physicist. We call this piece here the proper time because it's the time as measured in the reference frame of the experiment being conducted. On the other hand, in this case, we're looking at a cat in the reference frame of the physicist on the ground, right? Because the cat is on the ground. So that makes this the proper length. It's always important when you're completing a relativity problem to identify which frame is the proper frame, which is the natural rest frame of the thing you are observing, because that's what determines the proper time and the proper length. Meaning I need to solve this now instead for the length measured by the physicist on the train is going to be the proper length times square root 1 minus v squared over c squared. In other words, we get two very important results from this. This equation tells us that moving clocks run slow. And this tells us that moving rulers measure short. And we're going to see how that works out in an activity up next.
Well, this, believe it or not, is what the universe looks like from the perspective of a moving observer in special relativity. What you're seeing here is the world is seen by the red dot here. The red dot is moving, and I think it's an ellipse. Maybe it's a circle. Well, a circle is a type of ellipse. And what's happening is that length is being contracted in the direction that the observer moves. So as the observer moves down, length contracts in the vertical direction. As the observer moves to the left or right, the length contracts in the horizontal direction. And there's a couple of things happening with length contraction. For one, the size of each of these boxes is changing, right? You can see them getting thinner and stretching up in the vertical. Then they stretch out in the horizontal, again, depending on what direction you're moving in. But it's not just the size of the boxes themselves that changes. It's the actual space in between them. Length contraction, the contraction of an object as you move, is actually just a special case of spatial contraction, the contraction of the points in space. Let me show you how this program works. What we first do is set up the speed of light. So we're going to set it up to 3, so all the velocities are in units of 10 to the 8 meters per second squared. Here's our velocity as a function of time. Yeah, it is moving in a circle because it's moving as cosine and sine as a function of time. What we do down here is create some props. So we're going to set up a few of these rectangles in space, these rectangular prisms. We're going to set each of them at a different location. And then we have our relativistic observer here is going to be the sphere. First, we update the observer's velocity based on the current time. Then we update their position based on the velocity. The way this update works, it probably looks a little funny to you if you've never done any programming before. It's based on the velocity equation. It's based on velocity equals the change in position over the change in time. But what we're doing is we're reverse engineering this equation, because what I want is I want the new position, right? So I can think of this as the x new value minus the x old value. And it's like I'm dividing that by a small step in time. So this delta t here, this dt over here is just a small number. The smaller you make it, the smoother the animation will be. So what we've done is we've taken v and multiplied it by delta t. And then we're going to add to that x old. And that's going to get us x new. So in other words, I was at one location, x old. I want to move to a new location. And the way I do that is by adding on v times delta t. So this is the change in x. I'm adding the change to the old value to get the new value. The trick in making an animation is to have this thing repeat, is to take the new value, make that the new old value, and then add v times delta t to that again to get the new value, then set that to the old value, etc., etc. That's what's going on in this equation when I have this funny looking position equals position plus v times dt, right? You would never write this in a math class. You would never write x equals x plus a number in a math class unless that number were 0. But what this is doing, since it's a computer code, is it's saying, take this old value, add to it this new value, and then write over the position value with the new value, right? Because you don't need the old one anymore, you need the new one. And so this POS, this position, is tied to that relativistic observer, that sphere we created here. And so this line 41, this is the thing that is creating the animation. All the rest is just math and bookkeeping, but this is the thing that is keeping track of the animation. What's happening with the size of the scenery is we have a list of objects called scenery. So a list is literally just a whole bunch of items in one variable name. So scenery is a shorthand for a whole lot of variables that are these rectangles that we made earlier. And we're saying for P in scenery, so for each one little item in scenery, we're going to do this. So we're going to change the thing's size and position based on the Lorentz factor. So the gamma factor here, this is 1 over square root 1 minus v squared over c squared. This is that Lorentz factor gamma that we were working with in our length contraction and time dilation, the 1 over square root 1 minus v squared over c squared. It's here in the x direction, here in the y direction, here in the z direction, so that we're only contracting when we move in the x, only contracting when we move in the y, and only contracting if we move in the z, respectively. So we're changing the thing's size and we're changing the thing's position as we go around in the animations. All the rest of this stuff is just set up. This thing, this loop that's going to repeat over and over again, this is the thing that we are most interested in. And so based on whatever the velocity pattern is, we're going to get a different pattern for the contraction here. You might, for example, change the velocity. If you come up here, you might change the velocity to keep the velocity in the x direction at 0. So maybe we change this 2.5 into a 0.0, right? So whatever changes you make to here, it's going to impact the animation. So now we should only be moving in the y direction. And sure enough, we do. Our particle, our observer here, is only moving in the up and down direction. And what you notice in the animation is that we only contract in the up and down direction. We're not contracting in x and y anymore. We never contracted in z. If you didn't notice that before, we weren't contracting in z because we weren't moving in the z direction. And so here you can isolate the motion in the vertical direction. Or if you want to have some even more fun, you can give the thing a motion in the z direction. So maybe we do a little bit less motion in the z. Let's have that be a 0.5 times cosine. And let's give it a different frequency. Let's make it a little bit lower in terms of frequency times t there. And so now we'll see it oscillate in the z direction, but it's not going to oscillate as quickly. If I rotate out here, you can see I'm moving along in the x and y like before. And I'm kind of moving along the z, not nearly as much as I am in the x and y. And so we'll get a little bit of contraction in the z direction as well. Now, just a little bit, not as much as in the x and y, just a little bit. And so one of the things that you can do with this code, you can play around with the scenery. So you can just make a couple of props instead of this whole list here. I can comment that out. So the things with a hash mark in front of them, the computer is going to ignore because that's a comment. And so I can, for example, take this thing and just have a couple of, just one, that's actually just one, and just have one rectangle if you just want to keep track of the singular one there. And then you can also play around with the observer's motion to make it contract in different ways. So here's an activity to help you get started understanding length contraction and time dilation. The first step here just goes over all of the theory that we went over on the whiteboard. It talks about how the time transforms from the proper time, how the length transforms from the proper length. It'll ask you a few questions about just some simple stuff relating to those equations before we get into the code. For the units for this code, we're going to be working in units of c, which means if you have v equals 0.5 c, that means that the velocity is half of the speed of light. So it asks you a question there to help you understand what it's like to work with velocity in units of c. And finally, come down here to the computations. This is using a package called IPyWidgets, and I love IPyWidgets. It makes your code interactive and allows you to change numbers just by clicking and dragging. So after it imports a bunch of stuff, this is just importing other libraries that we need. We're defining a function, that's what DEF means, is define, called transform, where you give a proper time and a proper length and the velocity as in units of c. So let's see. Here what we're going to do, we're going to calculate the measured time. So this is measured time equals proper time divided by the square root of 1 minus v squared over c squared. This is exactly what we have up here for the time dilation. Time equals proper time divided by square root 1 minus v squared over c squared. It's just written in a way that the computer can understand. So slash is the same thing it means on your calculator. It's just a slash. This np dot square root means I want you to go to the np numpy library and look up the square root function. So numpy is a library that has all the mathematical functions you could probably ever want. And some more than you actually want. And so it's looking at the square root function and it's taking 1 minus v over c squared. For some reason, Python uses a double asterisk instead of a caret as an exponent. So whatever you want to do to a power, you just put in double asterisk there. Same thing with measured length. We take the proper length and multiply by square root 1 minus v over c squared. And then we're going to print the measurements there. So you are measuring in the proper time. Your partner is measuring in the measured time and measured length. And so what this command does, this print, is says, tell me on the screen what this information is. So this thing in the quotation marks means print this exactly to remind me of what it is that I'm looking at, and then print the value that you have stored in measured time. Same thing down here, print the partner's measured length. Here's where we're going to set up the interactive widget. So we're calling on the transform function. It requires 3 arguments, proper time, proper length, v over c. So I have to tell it what to do with proper time, proper length, and v over c. We're going to give each of those a slider with a minimum value, a maximum value, a step size, and then a description to remind me of what these things are. So when you run this, you just press Control Enter or press the play button up here in the upper left. It'll take it a second because it has to go and grab all those libraries from the internet. So here I've got my proper time, my proper length, and our velocity v over c. So this is the velocity of my partner with respect to me. And what you'll notice at first is that their time matches mine, right? Because our velocity is 0. Well, let's suppose they start to move. I could click and drag this out to give them a speed of, say, 0.1 times the speed of light. So remember, this is v over c. So a v over c of 0.1 means they're moving at 1/10 the speed of light. My partner's measured time is now a little bit longer than mine, right? Because moving clocks run slow. And their measured length is a little bit shorter than mine, right? Because moving rulers measure short, right? And so what I can do is I can click and drag this thing around to see what will happen to their measurements as they move faster compared to the speed of light. I can also click and drag my time value. Maybe I want to see what happens to the time here with mine. Maybe I want to move it to a 10. By the way, you can either click and drag on this, or once you have it highlighted in blue here, you can also press the arrow keys on your keyboard to move them around. You might notice I'm moving in steps of a half on this. That's because my step value on here is 0.5. If I wanted to make finer adjustments, let's suppose I wanted to move out in this second decimal place here, I could just change the step value to a 0.01. That's all you have to do. You don't have to write this code from scratch. You're just editing it. Then click Run. What you'll notice is that my T0 now moves in steps of 0.01, much smoother control than I had before. The L0 is still moving in steps of a half, right? Because I haven't changed its step value yet, so I can change that to a 0.01. Always remember to rerun your code cell before you expect any changes to happen. And now I can very finely control this thing with a step size of 0.01 there. And so as I click and drag to this velocity, I can get these things to change as well. You could also change this thing to be even smaller. It's probably okay in a 0.01, but we'll just leave it as it is here. And I can even make this thing negative, right? The velocity is getting squared up here, so it actually doesn't matter whether you're going in the positive or the negative direction. You get the same result either way. You can also take this thing up really high, right? I might take this thing up even higher to 80% speed of light, 90% the speed of light. Uh-oh, I have taken it past the speed of light and gotten an error. So one of the things you're asked to do in this activity is there a problem with these calculations, and how might we be able to check on it beforehand? I'll let you read up about that farther down here.